Okay. Good morning, everyone. How did your homework go? Do you have any questions about antiderivative? Please, let's usual get going. Put your questions in the chat. Chris. Okay. All right. So we look at all those 45, 59, and 62. Okay. Great. So we start by remembering the main ideas here. So antiderivative or indefinite integral of f of x dx. This nothing, that's a symbol that represents a function f whose derivative is little f. So that's really the idea. And the main formula, a lot of basic antiderivative are easy. The main one that we have to remember is the antiderivative of x to the n dx. And this is 1 over n plus 1 x to the n plus 1 plus c as long as n is different from minus 1. And it's the ln of x is ln the absolute value, and I told you I didn't prove it, but you have to accept that because sometimes you will need this x to be negative. So we need the ln of the absolute value of x when n is equal to negative 1. We saw other formulas, but the other ones are actually easier to know. So with this in mind, we're going to look at some problems. So we look at number 45. 45, what is 45? Okay. So here we have the integral of a secant square of theta plus secant theta tangent theta d theta. Okay, so this is at the surface, it looks very scary, but actually it's not, because this is really simple. First, we have a sum. When we have a sum, we can split the integral. So it's the antiderivative of that plus antiderivative of secant theta tangent theta d theta. And now we have to remember stuff. Okay, so what is the function whose derivative is secant square? So this is my question. And try to remember, just try to read which function its derivative is secant square. Anybody remember? Derivative of which function is the secant? Anyone? Absolutely, that's the tangent. Okay, that we've worked with it, and you should know it. So this one is nothing more than the tangent of theta plus antiderivative of secant tangent. Again, it's the same question. Which function has for derivative secant tangent? So it's a good problem because it reminds us the derivatives of those functions. So anybody again remember which function has for derivative secant tangent? We've seen it. I mean, I know that. Anybody remember? That's the secant plus c. So because the derivative of secant is tangent. Okay, so that's the difficulty of this problem, is really to remember that the derivative of tangent is secant square and the derivative of secant is secant tangent. All right, now we look at number 59. And 59. Okay, so that's the antiderivative of t plus 1 over t dt. Okay. All right, so here I have one function divided by another, so there is no rule for that or whatsoever. So we have to manipulate this so that I can rewrite it in a format where I can find the antiderivative. Okay, so that we have to rewrite. There is no other way out. So how can I rewrite this? Rewrite so I can make it into something I can find some antiderivative. Ideas. Right, so basically the easiest way is to break up. I have here a numerator, okay? Now, remember we can break up the numerator. So mainly if you have a plus, we can do this problem in two ways, and I will do it in both ways. A plus b over c is the same thing as a over c plus b over c. Okay, so we can break a numerator. We cannot break a denominator. So why I'm saying that? T plus 1 over t, this is t over t, plus 1 over t. That's the only way out. We have to manipulate it algebraically to get to something we know. So, which is equal to t over t is a 1 plus 1 over t. Now the problem is in a format that we recognize. Now I have a sum, and sum can be broken. So it's the antiderivative of dt plus the antiderivative of 1 over t dt. And this will give me antiderivative of dt. It means that's a 1, that's a t plus. That's 1 over t. We have to be very careful. When I have 1 over t, 1 over t, so that's the natural log. So that's the ln of t plus c. Okay, so that's how we can do this problem. Now, or you can do it this way. Which one is you more comfortable with? Or you can say t plus 1 over t dt is equal to the quantity t plus 1 times t to the minus 1 dt. Okay, either way, it doesn't matter. And now I can distribute. If I have a product, I don't know what to do. I distribute t times t minus 1, that's a 1, plus t to the minus 1, which is basically the same thing as that. And then I repeat what I did. That's 1 plus 1 over t dt, which is the t plus the ln. Okay. All right, so the main idea that if I'm faced with a problem like this, which we will, and we're going to learn, depending on the problem we're going to learn a lot of tools to do those. But for now, there is only actually one tool. Regardless what we learn, there's going to be only one tool for this problem. It's just we can split the numerator, and then it becomes really easy. And remember, I'm splitting numerator. I do not touch the denominator. You can never split denominator. Okay, now we look at 62. All right, let's see what 62 is about. So 62. Okay, so it's fairly similar to this one. So it's 10 t to the power 5 minus 3, the whole thing divided by t dt. Okay, so it's very similar to the one we did a minute ago. So I'm going to split the numerator, which will give me 10 t to the power 5 over t minus 3 over t dt. And that's my t. Okay, and now simplify a little bit more, giving me 10 t to the 5 over t, that's a t to the 4 dt, minus integral of 3 over t dt. Now I have a constant, and this is a constant. And we know one of the property of the indefinite integral that the constant, only constant, not variables, not t, can be taken out. So it's 10 times that. And 3 is a constant. I can do that for 3 as well. Now I am back to basics, and I can find the antiderivative. So it's 10 times. Antiderivative of that is 1 over 5, because here n is 4, t to the power n plus 1, which is 5, minus 3, ln of t plus 6. And finally, I will have 2 t to the 5 minus 3 ln of t plus t. I feel I did no. All right, and of the problem. Any other questions before we proceed? Okay, so today we're going to keep doing a little bit along those lines, and then we're going to move to section 5. And I would like to mention one thing. What we're doing for the last 2 weeks are the basics for 164. In other words, that if you mess up the last 2 weeks, you will not start 164 on good footing. You will have trouble, believe me. So I strongly urge you to learn this material extremely well, or you will not start calculus 2 well, and you will be in trouble for the rest of the semester. So please work with me very hard the last 2 weeks, as much as you can. So I'm going to ask simple questions at the beginning. So we have going to be the following. Suppose I ask you the following question. It's actually simple. Find a function f. Question number 1. Find a function f of x such that f prime equal to x, let us say, plus e to the x. Okay, so I'm asking to find a function whose derivative is to x plus e to the x. Is this a hard or is it an easy or a hard question? So instead of telling you find antiderivative, I'm giving you the derivative and I'm asking you to find the function. All right, so how are we going to do that? I'm going to write something and tell me before I write it, I'm going to ask you the question. What is the antiderivative of f prime of x dx? Back to you. This red box. What's the antiderivative of f prime? F. Do you agree with Zach? Absolutely. It's f because by definition, what's the antiderivative? It's the function. When you differentiate it, you get f prime. Which function, when you differentiate it, you get f prime is, of course, f of x itself. Okay. So if I want f, what is f? F is nothing more than the antiderivative of f prime. Of course, up to a constant, but we're going to take care of that in a minute. So f is nothing more than the antiderivative of 2x plus ex dx. So f is, we find that's 2x dx plus ex dx. Now 2 is a constant, so f of x equal. 2 is a constant, I can get it out. Antiderivative of x is a half x squared plus the antiderivative of ex is ex plus c. So as we know, there are a lot of functions whose derivative is that x squared plus ex plus c. Okay, so there are a lot of functions. There are a lot of functions whose derivative is 2x plus ex. Okay, now suppose I zoom in. Actually, graphically, what's really happening? What is f? And we know, as I mentioned before, there are a lot of them. Like, let us say, if I take c equal to 0, is x squared plus ex. Now, I don't know exactly how x squared plus ex looks like. So I'm going to just invent a graph. It's going to probably look something like that. So this is one of them. That's x squared plus ex. But as we said last time, every time you switch, you translate up and down, you're going to create a new one. So I don't have one f. So what I wrote f is wrong here. I have a lot of them. Shifting it one, shifting it. I'm creating another one. Shifting it down, I create a third one and keep shifting. So I have a lot of them. So my second question is the following. B. So I have a lot. Find f of x. Sometimes we call those problem initial value problem. Okay, find f of x such that the derivative is 2x plus ex. So I want the function derivative of that, and I'm going to put an extra condition. And I want the function at 0. Let us say I wanted to take the value 3. Okay, so this now I'm really putting conditions on the function. I want its derivative to be to x plus ex. It means the function has to be one of those. But now the other restriction of all those, there are a lot of them, I want the one who takes 0 to 3. So there are a lot of them, and I want the exact one that takes 0 to 3. Okay, so very, very specific condition. So how are we going to do that? All right. If I want f prime to be to x, if f, that's f prime, it means from the previous work, f has to be x squared plus ex plus c. That's what f of x is. But now I need that this f to satisfy f of 0 equal to 3. So I'm going to pick up the value of the constant that makes the function take 0 to 3. So we know, so we're going to find c such that the function takes 0 to 3. So for all those, I'm going to pick this particular one. So it's actually simple how we do that. Okay, I plug in 0 for x, and I force the condition f of 0 equal to 3. So I'm going to have 0 plus e to the 0 plus c equal to 3. Now I solve for 3. 1 plus 6 equal to 3. C is equal to 2. So it means my function f that satisfies this condition and this condition is x squared plus e to the x plus 2. Okay, we call this sometimes initial value problem. So for all those functions, if I go back here, there are a lot of functions whose derivative is to x plus ex. The one I want is actually the one that at 0 takes the value 3. That's the one I want. And what we solve for c, and we realize the one I want is x squared plus ex plus 2. That's the one will satisfy this condition. At 0, I will have 0. E to the 0 is 1. Plus 2, it takes the value 3. All right. So we're going to do, so those problems are actually fairly simple in nature. So we're going to do another simple one. So now find f such that, I'm just going to pick something, f prime of x equal, let us say, x squared plus 3x, and f of 1 equal to 2. So we don't have to give you always the value at 0, even though a lot of time the value at 0 is given, but we're not going to restrict ourselves. So I need a function whose derivative is this and take 1 to 0. So first I find the function, and we know that a lot of them. So f of x is the antiderivative of f prime. It means the antiderivative of x squared plus 3x. So which is equal to antiderivative of x squared plus the antiderivative of 3x dx. All right, antiderivative of x squared is simple. A third x cubed plus 3 is a constant. Antiderivative of x is a half x squared plus c. So I get f. So my f is a third x cubed plus 3/2 x squared plus c. So every function whose derivative x squared plus 3x have this form up to a constant. But now of all of them, I want the one that satisfies this condition. Okay, so now I say, okay, now we're going to find the c such that my function will take 1 to 2. Means I plug in 1 for x, and that's at equal to 2. So it means that, what is f of 1? I plug in 1 in the expression. It means a third, 1 to the power 3, plus 3/2, 1 squared, plus c equal to 2. And now I solve for c. So I'll get a third, plus 3/2, plus c equal to 2. Now a third plus 3/2, so this gives me a 6. And I have to multiply this by 2, which is going to give me a 2. Multiply this by 3, 2 plus 3, which is an 8. plus 6 equal to 2. It means C equal 2 minus 8 over 6, so which is 4/3. It means, which is equal to 2/3. So my function f is 1/3 x cubed plus 3/2 x squared plus 2/3. Okay. Questions before we proceed? Any questions?
I have one question.
Oh, please go ahead.
So we always have to, if we're given the prime, f prime, we always have to find the antiderivative first and then.
Absolutely, absolutely.
Okay.
If they want f, first you find what is f. That's the f prime. You can find it up to a constant because there are a lot of them. And am I doing a stupid mistake? I usually trust you guys.
I think, yeah, I think they're saying it should be 11 over 6 or
this one. Let's see.
I think
3 plus 9. Of course, I always do stupid mistake like that. You're not allowed. I am allowed. And that's give me 12. Thank you very much. So give me 12 minus 11. 1 over 6. 1 over 6. Thank you very much, guys. Any other mistake? Very good. Now, again, along the same line, we'll make it a tiny bit complicated. So now my question is, not much. Find a function f such that f double prime of x equal, I'll take a simple one first. F double prime of x equal, let us say cosine x. No, actually I said I'm going to take an easy one. Equal x squared. Okay? Is this a hard or an easy problem? How can you do it? Quickly. Now I give you the second derivative. Remember, second derivative is the derivative of the derivative. So how can I find a function whose second derivative is x squared? What can I do first?
Find the antiderivative of the second derivative.
Yeah, this will give me what, quickly?
The first derivative.
Exactly. So I have to find the first derivative first. There is no way out. And the first derivative is the antiderivative of the second one. Okay, because that's what the second derivative is. All right, so this is gonna give me the antiderivative of x squared dx, which is 1 over 3 x cubed plus a c, a constant c. There is a constant because there are a lot of functions whose derivative is x squared, everything of this form. And remember, c is a constant. It's crucial. Constant means it doesn't depend on x, just a constant. Very good. Now I found f prime. Now I need f. F is the antiderivative of f prime. It means it's the antiderivative of 1/3 x cubed plus c dx. Okay, so it's equal to what? I have a sum. I can split. So it's 1/3 x cubed dx plus the integral of c dx. So this is equal to 1/3 is a constant. I can pull it out. X cubed dx. My c here is a constant. Important. Otherwise, I can't pull it out. So I can pull it out. Dx. So this is constant. Okay. So finally, I'm done. So I will have 1/3. Antiderivative of that is 1 over 4 x4 plus cx plus another constant. What can I call this other constant? I'm not going to call it c because it's a totally different constant. They don't have to be the same. I call it d. So my function is, so two constants will be involved. So if I have the second derivative, okay, the first, the function will have two constants. So f of x is 1 over 12 x3 plus cx plus d, where c and d are constant.
How'd you get x to be 3 instead of 4 now?
Did I do another stupid mistake? Ah, this
I'm
one?
not sure. Yeah.
Yeah. Okay, very good. Now let us check. We have to check. Just I have to convince you that, you know, we do have a two constant. First, I need f prime is 1 over 12, that's a constant, times 4x cubed plus derivative of cx is c. Derivative of d is 0, so it's gone for f prime. So this is going to give me 1/3 x cubed plus c. Now I need f double prime. So as f double prime is 1/3 3x squared plus c. 3 and 3 cancel each other out. I'm going to plus 0 because c is a constant. I get x squared. So having two constant is actually makes sense. The first derivative will get rid of the first constant. Then my second derivative will get rid of my second constant. Okay. So if I have the second derivative, I need the function. Two constant will be in the picture. All right. Now I'm going to do the same thing as I did in the previous part, in the following manner. So find f such that double prime equal x squared. So now I'm gonna, we call those initial value of problem. But now I want, of all those functions, a particular one. And since I have two constant, I'm gonna give you two conditions. Otherwise, if I give you one conditions, you're gonna be able to solve for one of them. So I'm gonna find f such that the second derivative is x squared. And let us say the first, this is the second derivative. I want the first derivative, I'm going to pick easy stuff now, equal to 2. And I want the function to take the value 3 at 0. Okay, so now I'm going to, so this is what we call initial value problem. Initial value problem. It means it's a problem where we have initial value. It means we have value at 0 and we have the function at 0. So how I'm going to do this problem? Okay, so I'm going to throw the other one away. I'm going to do this problem again. So now I'm not asking you the general function. I'm asking you a particular one that satisfies this condition. All right, how do we do this problem? So I said, okay, what is f prime? F prime is antiderivative of x squared. It means it's 1/3 x cubed plus a certain constant c. Okay, but now before I find f, to make things a bit easier, I say, but I want f prime at 0 to be equal to 2. So of all those derivatives, I want one that takes 0 to 2. So let us find c. So before I proceed, I find c at this stage. Okay, let us find c. So I will plug in 0 in the expression of the derivative. I want this to be equal to 2. So this will give me my c to be 2. So now I have f prime is 1/3 x cubed plus 2. So that's f prime. So I found the derivative that satisfies this condition, because I want really a particular function, not the most general functions. Now I said f prime. Now I said, okay, I want f. So I want f. My f is the antiderivative of f prime. It means antiderivative of 1/3 x to the 3 plus 2 dx. Now I have to find that. So it is 1 over, because we did it a minute ago. I will go a little bit faster. plus antiderivative of 2 is 2x plus a certain constant t. Now I want my f to satisfy my initial condition. I want f to take 0 to 3, but I want f of 0 equal to 3, so we find d. There are tons of functions who have this as at the second derivative. I want the particular one. I want a very specific one. Okay, but f of 0 equal to 3, so it means I plug in 0 for 3. I get 3. So this would give me d equal to 3. So now the function I'm interested in is 1 over 12 x to the 4 plus 2x plus 3. Okay. Now we can check our work. What do I mean by check? Checking in this case requires you to check 3 things. First, check that the second derivative is x squared. That's easy. Then we have to check that my function takes 0 to 2. If I plug in, takes 0 to 3. And it does. If I plug in 0 for f, I'm getting 3. And then I have to check in that my function takes f prime at 0 to 2. So let's check that. What is f prime? F prime is 4 over 12 is 1/3 x cubed plus 2. So plug in 0, I get 2. So now I created a function. The second derivative is x squared. It takes 0 to 3 and take f prime of 0 to 2. Okay. So this is how we solve. I'm listening.
All right. So when we find the f of x, we take the derivative of the f prime of x that we just found in the last part of it.
Yes.
The 1 over 3rd x to the power 3 plus 2.
Exactly. Because I have initial condition. If I didn't have those conditions, what should I do? I keep the c.
Oh, so okay.
Okay.
But since you have the condition, you have to take the one that you just found. Yes, because
it will be easier. Exactly. So let me take you back to the first one I did. In this problem, did I give you any conditions?
No.
No. There's no condition. Just find a function, and there are tons of them. In this case, I have to keep the constant because I don't have any initial condition, nothing. And then I have to keep dragging it. There is no way out. You with me? Then I have the cx. Yes. I have to keep it. And then I have to find, once I find this, I have to find f. I have another constant. So if I don't have any initial conditions on the problem, I have to proceed this way. I don't have any other choice. I have to show that I have 2 constants in the picture. There is no way out. If I have initial conditions like here, I have f prime, and then the easy way to do it, okay, you find f prime, but then you say, but they wanted f prime to be 0. So let's find a constant that will force f prime to take 0 to 2. So I found c. Okay, and then once I do that, I will do exactly the same for f. So it depends on the questions. If you have initial conditions, you have to proceed this way. That's the easiest way. If you don't, then you have to give me 2 constants because there are 2 constants in the picture. Answer your question? Hope so. Okay. All right, my last problem along those lines before we move on to chapter 5. I have to start chapter 5 today. My last question is find f. Now, as you guys can imagine, I can give you the 3rd derivative, but I won't do that until you find the function. In this case, there will be 3 constants, but we're not going to do that. So I want a function such that the second derivative is, let us say, cosine x minus 2 sine, and I want it to satisfy the following initial condition. I want the derivative at pi to be 3, and I want the function to take pi to, I don't know, like to 4. Okay, so let's do that. So first I need f prime. F prime is the antiderivative of the second derivative. Okay, so it means the antiderivative of cosine x minus 2 sine x. Okay, so let's do that. Okay, the antiderivative of cosine is the sine minus 2, that's a constant. The antiderivative of sine is minus cosine plus a constant c. So this will give me sine x plus 2 cosine plus c. So that's my f prime. But now because I have initial condition, otherwise I have to keep my c, I said, okay, but I want f prime to take pi to 3. So let us find the c that will force f prime to take pi to 3. Okay, so I plug in pi into the expression here, plus 2 cosine pi plus c. I want this to equal to 3. Now I find my c. Cosine pi is 0. Cosine pi is minus 1 plus c equal to, this is minus 1. This will give me that c equal to 5. Okay, I got my c. So now I have my f prime. I have f prime, which is sine x plus 2 cosine plus 5. So for all the function whose derivative is cosine x minus 2 sine x, the one that will take pi to 3 is this one. So that's the particular one. Now I need f. So I got f prime, now I need f. What is f? F is the antiderivative of f prime. It means the antiderivative of sine x plus 2 cosine plus 5 dx. And now again I proceed. I'll do it one by one. Antiderivative of sine is minus cosine plus 2 is a constant. Antiderivative of cosine is sine plus 5. Antiderivative of dx is x plus a constant t. Now again, I play the same game. I say, okay, but of all those functions, I want a particular one. I want the one that will take pi to 4. So we're going to find the d. So let us find the d. So I plug in pi for x, so I will have minus cosine pi plus 2 sine pi. So this is, I'm saying that f of pi is equal to 4. That's really what I am doing. So I'm plugging 4 in here, pi in here, plus 5 pi, because x is pi. So this x is pi, plus my d. I want this to be equal to 4. And now I substitute. Cosine pi is minus 1. Minus minus, it's a 1. Plus the sine pi is 0. Plus 5 pi plus d equal to 4. And now I find my d. So my d is minus 1. So it gives me a 3 minus 5 pi. And finally, my function is minus cosine x. So that's my function. And I found a particular d that will send pi to 4 plus 2 sine x plus 5x plus 3 minus 5 pi. And that's my function. Okay, so it's not really a hard process at all, but it's just finding antiderivative. That's really what is it about. Now the application to that is, I will tell you what the application is for it, and then you guys, I'll give you problems along those lines. Okay, one of the main application for that you guys will definitely see in your physics courses is the following. And I will tell you what it is and I'll assign problems. So the main application is the following. Okay. Let us recall from the beginning of the semester. So suppose we have an object moving along a line. Moving along a line, it could be vertical or it could be horizontal, but it's a line. And S of t is the position function. It means a function that tells you where the object is at every moment in time. S of t is the position function. Okay. Now, what we know is that the velocity, so v of t is the velocity at time t. And a of t is the acceleration, how fast the velocity is changing. Okay. And now let's see what's the relationship between all those three functions. Let us remember. So what we know is that the derivative of the position function, we differentiate the position. It means this tells me where the object is, which is also give me an idea what the distance traveled over a short period of time. The derivative, which is change, which is distance over time over a short period of time, give me the velocity. And let us remember that the acceleration is the derivative of the velocity or the second derivative of the position function. Okay, so these are the relationship. So where is our application to that? So suppose I give you the velocity. That's really the idea. I have an object and I give you a velocity. Can we find the position? So now we're moving backward. If I know how fast the object is, I know the position of the object. What does this give me? If I know the acceleration, I know the velocity. If I know the velocity, I know the position function. Okay, so you guys will have problem along those lines where the velocity will be given to you and you'll have to find the position. The acceleration will be given to you, you have to find the position. And in physics, most of the problem, we will know the acceleration. And that's really what's happening here, that the acceleration will be given to us by one of Newton's law, because Newton's law tells us the force is mass times acceleration. Okay, for those of you who have no physics. So a lot of time we know the force that's causing the object to move. So we will know the acceleration. So physics actually a lot of time lend itself into a formula for the acceleration. So now our question is, okay, if I have this object and I know the acceleration, it means how fast the velocity is changing, can I find a function which tell me the position? And this process will help me to do that. So if I know how fast the velocity is changing, or I know the acceleration, and this is usually come from physics, and then I will be able to find the position function. And that's really the main, one of the main application, one of them. You guys will see tons of application for that eventually, and that's one of the application for those problems. Okay, so I will give you a problem where either the velocity is given or the acceleration, and I'm going to ask you to move backward and find the position function. All right. So today we're going to start a little bit, move on to section 5. And we're going to relate it back to this antiderivative things we're doing later on. So, so section 5, chapter 5, let me give you the title. And it's about what we call definite integral. I think that's what they call it. Definite integral. So what we've saw so far, this is called indefinite. We're going to introduce something called definite integral, and then we're going to relate it to our indefinite integral. But this has to wait a little bit. The first section, which is section 5.1, is something called approximating area. Approximating area. Okay. All right. Before I do approximating area, which is I'm gonna take in details tomorrow, I would like to introduce, some of you I think may know it, the sigma notation, because it's a notation that we will be using quite a bit now, and you guys will use in 164. So sigma notation, which is the following. So let's do sigma notation. Sigma notation. Sigma notation, it's a way to represent a sum. So it's kind of, we have a sum, adding lots of numbers. We want a way to represent them. So I will give it in a first formal way, and then as example. So suppose I have a bunch of numbers. I'm going to call them A1, A2, bunch of numbers, etc., AN, bunch of numbers. Okay. And I take those numbers and I add them. Okay, plus, blah, 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 plus, plus. So let's assume you have 100 numbers. I'm going to add those 100. So it's sometimes tedious to write a 1 plus a 2. So the sigma notation, it's a way to, a simplified way to write this. So it goes like this, sigma. That's the symbol for sigma, which is the letter S in Greek. That's really what's coming from. Sigma, I will write A, and an index here, AI, I equal 1 to n. AI, because this here is changing. 1, 2, 3, 4 is represented by AI. Okay, so let us a little bit practice this notation. So for example, suppose I have the following sum. 1 plus, I'm going to write it in a 2 square plus 3 square. So I'm going to add those numbers and I'm going to keep adding them. Let us say 10 square. I'm not going to evaluate, but I have a sum that look like that. So how can I rewrite this? I'm going to rewrite it using the sigma notation. So it's a way a little bit to write this sum in a more compact way. All right. How can I write it? First, we have to watch the pattern that I'm really talking about. So according to my picture, this is the A1, if you want. This is the A2. This is the A3. And this is A10. That's really according to the sum. But what is the pattern that's really going on here? A1 is 1 square. A2 is 2 square. A3 is 3 square. So how I'm going to write this? I will write the first one and then the rest will be easy. We write this in the following format. Each one has the form. What's changing is the 1, the 2, the 3, the 4, the 10. Each one has the form. A certain I to the power 2. That's the format. Where my I goes from 1 all the way to 10. Okay, so what is really changing? We look at the sums changing. It's a 1, it's a 2, a 3, 4, and 10. That's really what's changing. And that's 1 plus the 2 square, 3 square. So the way we're going to represent them is sigma I square, I equal 1 to 10. Let us read this backward. What does this mean? If I is 1, that's a 1 square, which is 1. Plus, if I is 2, that's 2 square. Plus, if I is 3, 3 square. Plus, etc. If I is 10, is 10 square. Okay, I'll give you a lot of other problems so you guys will figure it out. So suppose I give you a half plus 2/3 plus 3/4 plus 4/5 plus, let me say 5/6. I'm going to stop right there. And those have a pattern. And I want you to write this in sigma notation. Okay, how can I write those in sigma notation? First, we watch the pattern was changing. 1 over 2, 2 over 3, 3 over 4, 4 over 5, 5 over 6. So how can I write this as a sum? What type, how's the term changing? Anybody can see anything. So there is a pattern. I'm gonna actually kind of catch it in here. I over I plus 1. So what your classmate is telling me, okay, 2, 3, 4, 5, 6, and this is 1, 2, 3, 4. So the numerator is like in I, and my denominator is 1 plus the numerator, I plus 1. So this is the kind of terms we're adding. And my I goes from where to where? And here I have to check. I start at 1. So if I is 1, I'll have a half. And the last I is equal to 5. So now let me go backward and make sure I'm doing it right. If I is 1, I will have 1 over 1 plus 1, which is a 2, plus 2 over 3, plus 3 over 4, and so on and so forth. Okay. All right. Let me, okay. Now I'm gonna move backward. More example. Suppose, and the question is, write it, not computed, but write it explicitly. Write it explicitly. I'll explain what. Okay. Suppose I give you the following. Sigma I equal 1 to 10. And I want you to write it as a regular sum without a sigma notation. All right. What is this as a regular sum? Okay. Let's see how to read it. I say, if I is 1, I start from 1. If I is 1, this is 1. Plus, if I is 2, this is 2. Plus, if I is 3, this is 3. That's how we read it. Plus, etc. I keep going. If I is 10, I go all the way up to 10. One more, and then, of course, we stop. Suppose I give you sigma 2. Instead of writing I, I'm going to write 2k plus 1. And I'm going to start k at 0. And I'm going to finish it at 5. Let's read this clearly. How do we read this? I don't have to use I. It's like a function. I don't have to use x. I don't have to use I. I can use any letter I want. I can't reread it. If k is 0, I plug in 0 in here, I get 1. Plus, so that's k equal to 0. Plus, if k is 1, I plug it here. 2 times a 1, 2 plus 1, that's a 3. Plus, if k is 2, I plug in 2 in here, I get a 5. Plus, if k is 3, I plug in 3 in here, I get a 7. K is 4, I plug it in here, I'm going to get a 9. And finally, if k is 5, I should put it here actually, k is 5, I get 2 times, I get 11. So that's how the sigma notation is read. That's how we read it. And that's how we go backward. Okay, so it's a notation that we're going to start using. All right, that's it for today. I will put your homework up on my lab once we finish. And see you tomorrow. Bye-bye, guys. Thanks.